Greetings. Welcome back to my video series on magnetism for AP Physics C, and in this video I'm going to be covering magnetic fields generated by currents, not to be confused with what we covered in the last video, which was magnetic forces acting on current carrying wires. There's a bit of a difference between the two, but they both play into exactly what causes magnetism in the first place, which is moving charges. So without further ado, let's get started. And again, the big key player here is the fact that moving charges are the things that generate magnetic fields. Just like charges experience forces from and create electric fields, and masses experience forces from and create gravitational fields, moving charges experience forces from magnetic fields, but they also happen to create magnetic fields in the process. And so again, I mentioned in the previous video that this was a pretty basic observation that was made around the mid-1800s by one Hans Christian Ørsted and André Marie Ampère. And the observation was that if we ran current through a wire and we placed different compass needles around that wire, generally the more current that runs through that wire, the more clear it's going to be that the compass is orienting itself in some fashion around that wire. Namely in a circular pattern, if you were to look at it from the top down like this. And so the main takeaway from that was that, well, if we're pushing current through this wire and it's skewing the compass, those currents are generating some kind of a magnetic field. And compasses, already being a device that allows us to measure the effects of magnetism pretty accurately, compasses were a great way to help us visualize exactly which direction these fields were pointing in around that wire. And later on, kind of around the same time period, a very famous physicist, Michael Faraday, whom we will talk about very much later, created that famous technique that you see oftentimes with magnets in pouring iron filings over a magnet to let all of the filings act as mini magnets that align themselves with the field. In doing that, you can get some really beautiful demonstrations of the fields generated by different combinations of wires, things in coils, things in loops, solenoids, toroids, all sorts of different combinations. We were able to study and understand really well exactly where these fields were pointing, and that's pretty beautiful. So all of this led to, funnily enough, another right-hand rule that we could use to make sense of the fields that were being generated by a wire in any given orientation. So the main thing is that magnetic fields seem to circulate around current-carrying wires concentric to that wire. And so the right-hand rule to make sense of that involves making a thumbs up with your right hand. So the step-by-step process here is that you make a thumbs up with your right hand, you then take your thumb and you point it in the direction of the current, wherever that may be, and then basically you're done. Because after that, really your fingers are naturally curling in the direction of the concentric circular path that the magnetic field lines are taking around that wire. Now here, this kind of relies on the wire being straight the whole time. We will have ways to make sense of the magnetic field direction of not straight wires later on, but that's something for a future video. For now though, if it's a straight current carrying wire, or it's roughly straight, at least in the region we're trying to analyze, then this right-hand rule works very well. And it's worth noting that, again, this is to visualize the magnetic field lines. So if you want to visualize the magnetic field vectors that are generated, which is what you'd probably do your math with, well, those vectors are tangent to the path at each point. So you're thinking of, like, if you were to go around a circle along these field lines and then suddenly just break off from the circle and keep going in whatever direction you were going at that instant, that's the tangent line. So if I were to start here and then fly off, I would be flying off tangent in this direction, off that way. Or if it were over here, this way. If it were over here, I would fly off this way, and so on and so forth. Tangent means kind of off away from the circle, wherever you were last going. All right, so with this is a pretty important right-hand rule to have a good feel for, because a lot of the time, as we'll see later in this video, you're gonna have to do a little bit of gymnastics with figuring out the direction of a magnetic field, and then subsequently figure out the force that that magnetic field generates on another charged object in the problem. And so you have to keep switching between all of your different right-hand rules and different scenarios. And amazingly, this is still not the end of different right-hand rules that we'll have to use in this unit. So for now, I'm just going to help make sure that you have a good handle on this right-hand rule. So let's do a little bit of practice to help out with that. All right, so I've got 3 situations here, each kind of slightly adding an extra bit of oomph or zhuzh into the scenarios. So this first one here is just a simple wire. And the main purpose of this one is I just want to show how I like to represent the direction of the magnetic field when you're presented with a situation like this. All of this is to help construct tools to give you better places to apply different right-hand rules at different stages in the problem. And so this is good practice for things that we'll need to apply later on. So with this first one, we have a wire whose current is pointing to the right. And so for this, all we need to do is put up a thumbs up. And then at this point, you just need to take your thumb and point it in the direction of the current. And then again, your fingers are going to curl in the direction of the magnetic field around that wire. And so normally when I like to do this, I like to look at 2 main anchor points. One is, are my fingers on top of my thumb pointing towards me or away from me? And then at the same time, if I were to kind of curl my hand a little bit more down, once my fingertips are below my thumb, are my fingertips going into or out of the page? And so in this case, with your thumb pointing to the right, on top, your fingers should be coming towards you, and on bottom, your fingers should be going away from you. And so here, to make sure that we keep track of that and we draw it and have it set in stone, we're going to say on top, the vectors should be coming out of the page. So they're going to be drawn as dots, going by the convention set up in the previous video. So out here, I'm just going to draw dots, indicating that the field lines are coming out of the page above the wire. And then below the wire, well, the field lines, if we're kind of imagining them along here, they're going to be kind of wrapping around in a circular path. I'm trying to keep my perspective accurate here. And so on bottom then, the field lines are now going to start traveling into the page by the time they've reached this destination. So we'll have field lines going into the page, in which we are looking at the back of a literal arrow. We're looking at the feathers of the arrow flying away from us. And really, with a setup like this, that's really the most useful thing. If a problem is giving you a wire in this perspective, odds are you're needing to apply the direction of the magnetic field above or below this wire. However, it is just important to know that it is traveling in a complete circle around. And so if I were to draw the complete picture for this, it would kind of loop back around, would go back up here, and the magnetic field lines would be kind of going upwards on the other side of the wire, what's being eclipsed by the picture. And so here, just keep in mind that there's pretty much a continuum of circles all going around this way. And if you were to expand this out, there would still be magnetic field lines going into the page right here and out of the page right here, further out. So normally this is all just designated by some random distance r that is normally given to us in the problem. All right. So then moving on to this next one, we have now 2 wires, both whose currents are going into the page, since we're looking at the back of an arrow. And here our goal is to figure out what the net magnetic field is at this location P right here. So in this case, again, I'm going to color code so we can distinguish between the 2 wires a little bit more. But again, the first thing we need to do is figure out and draw the magnetic field lines that are being created by these wires. That's going to help us visualize where we need to draw our vectors. So in this case, again, make a thumbs up. And here, because the currents are going away from us, they are going into the page. So you're going to take your thumb and turn your hand around so that your thumb is pointing into the page. And in this case, your fingers are going to be curling in a clockwise direction if you've done that right. And so with this left wire, clockwise is going to look something like this. And I'm going to try intentionally to intersect my circle with point P for a very important reason later. All right, now that's not the best circle ever, but it gets the job done. And then on the left, we're going to do the same thing. Now keep in mind again, this current is also traveling into the page, so the magnetic field lines generated by this guy are also going to be traveling clockwise. So I'll make another circle and I'll try to do my best to make it concentric with the wire. But again, it's not an exact science. Well, it is, but it isn't here. And that looks pretty good. So now, just to seal in stone that this is traveling clockwise, I'm just going to draw a few arrows reminding myself that, yeah, everything's going in this direction all the way around. And it's the same thing for this guy over here. Cool beans. And now here's the advantage of doing something like that. Yes, you took probably a lot of extra calories to draw those circles, but at point P now, it's a heck of a lot clearer which direction these vectors at point P are going to be going in. Remember that magnetic field vectors are always tangent to the field lines. And so in this case, the vector created at point P by this left wire is going to be traveling tangent to this circle, which we could say is probably down and to the right this way. So that's B1, let's call it. And then the magnetic field vector due to this guy, B2, is going to be going up and to the right, tangent to this circle at that location. Now, because I didn't treat it like an exact science, my vectors are not perfectly symmetrical, but in a scenario like this, the symmetry would definitely come into play here, just like it would in a similar problem with electrostatics. So where you could go from here, if you wanted to find B net, is you could argue that these vectors, when added tail to tip, are going to add in the x direction and cancel out in the y direction. And so if that's the case, then really whatever the x component of both of these vectors is going to be our net magnetic field in this case. So we would have B1x plus B2x as our net magnetic field. Now, we can't get into too many more specifics besides that without having more information available in this scenario, but just keep in mind that all of this does lead to vector addition in some way, even if we're starting with circles. So it's just something worth keeping in mind. Now, with this last example, now we have another charge adjacent to a wire that's in motion. And this is where the stuff we were doing for this first example is going to come in handy, because here I'm going to add in the extra step of figuring out what force this wire's magnetic field is exerting on this electron traveling downwards. So to start with this, say we want to figure out the force on this electron. I'll go ahead and write that as our objective. Well, we have a couple of steps we need to take along the way. First, we need to figure out what magnetic field this electron is in. What direction is it going in? Because in order to figure out the force that this electron is experiencing, we need to know the direction of the magnetic field that it's in. And so to start, we're going to take a look at this wire and, well, you guessed it, we're going to put our thumbs up. And in this case, we're going to make a thumbs down because the current is traveling downwards. Now, in this case, clear as day, our fingers should be curling kind of in the into the page direction to the left of the wire. So I will go ahead and enter that into the mix. I'll make the electric field vectors green in this case. So not electric field, magnetic field. So if they're going into the page to the left of the wire, then I'm going to draw a bunch of X's to the left. And then if our fingers are curling around the wire, then when they reach the other side of the wire to the right, that means that these magnetic field vectors are going to be pointing out of the page. So it's going to be represented by a bunch of dots, like so. And it's okay to have them overlap a little bit, and maybe useful even to draw dots off to the side, just so we can be sure. And then again, just keep in mind that in this perspective, we still have magnetic field lines that are traveling in a complete circle around this wire. It's just that we only really care about the left and the right, but in this perspective. So in this case, we have the direction of the magnetic field. So now if we want to find the force on the electron, we have to call upon our previous right-hand rule for magnetic force, which is more of a finger gun than a thumbs up. Now there's one extra trick here, which is that the electron here has a negative charge. And recall that with our right-hand rules from the last video, you use your right hand if you're looking for positive charges or currents in wires, but you use your left hand if you're working with negative charges, which we are here. So with your left hand out, again, our index finger is the direction of the velocity of those charges. Your middle finger is the direction of the magnetic field, and the thumb will then point in the direction that the electron is going in. So in this case, we're going to take our index finger and we're going to point it downwards to lock in our velocity direction. And then we need to take our middle finger and point it out of the screen Since we're looking at dots, we're looking at the arrow flying towards us. And in that case, once you've got it set up, our thumb should be pointing to the right from your perspective if you're following along with this. And so in this case, the electron is going to be experiencing a rightward force due to this current carrying wire. And so I will go ahead and draw the magnetic force pointing to the right on this electron. Cool beans. So these three examples all contain something a little different, but it's all kind of based on the same logic. You just really want to get comfortable with using your right hand or your left hand in certain cases for the appropriate right hand rule at the time. It's really important that you practice these often, because being able to freely jump between these back and forth is going to make solving these problems a heck of a lot easier in the long run. So there's one more thing we need to cover, which is how exactly we could get maybe a value for this force. And to do that, we need to figure out the magnetic field strength at the location of this electron. So let's try out something that might help us do that. Now, having a good understanding of how magnetic field lines are generated by those wires is one thing, but because we had a pretty good experimental process for analyzing those fields, there was also a pretty easy way to model this field as well and create an equation for it. So, of course, that's what they did. Here, if we just put another wire in the vicinity of this other one, then we have a pretty good way of measuring the force. And with that, we can kind of work our way backwards to figure out how strong the field generated by a wire actually is. So modeling this, we created this equation for the magnetic field produced by a current carrying wire. So the magnetic field B is equal to this constant times the current in the wire I divided by 2 pi times the radial distance from the center of the wire. So this would be just the distance away from the wire if you were starting at the center. Now that constant I kind of glazed over. That is another fundamental constant of the universe called vacuum permeability. That's how it's referenced on the AP Physics C formula sheet, but other times you will see it named the permeability of free space, which is really the same thing. Now this is how the constant appears on the AP formula sheet, and it plays into how convenient the number associated with this constant is. The permeability, or the vacuum permeability, is 4 pi times 10 to the negative 7 Tesla meters per amp. So 4 pi is pretty easy to remember, although since it's on a formula sheet, you don't really need to remember it. But this is a constant that's very similar to the kind of cousin of this constant that we had in electrostatics with the permittivity of free space. They're both very closely related, and there's something we can do that's rather magical to link these two together later on. But for now, just know that this constant is here, and it is quite important for calculating the magnetic field due to different things, especially through this law or ones that we will talk about later. Now, the other thing I want to emphasize is that, again, because these fields are being created in circular paths, well, it's not just one circle away from this wire. It's really a continuum of circular paths all created around this wire, each with some distance r away from that wire. Now, in each concentric circle, all points around that circle all have the exact same magnetic field strength, B. And really the only difference is the direction is constantly changing, tangent to the circle at all points around that path. So with that, I'd like to show how we can use this equation in tandem with some of the equations from the previous video with magnetic force to show how we can figure out what force two wires exert on each other. Now, this was a pretty clear experimental observation that was made by physicists when they were first characterizing all of this stuff. Well, I mean, if we think about it, current carrying wires at this point experience forces from magnetic fields. We established that in the previous video. And they also create their own magnetic fields, as we just established. And both of these are tied together pretty nicely, because then if you have one wire that's generating a magnetic field and another wire that's carrying a current, then it's going to experience a force due to that wire that created the field. So if we say this left wire here is creating a magnetic field due to some current, I1, and this other wire is carrying some sort of current, I2, in the same direction, well, the field that this one creates and overlays on top of this other wire is going to result in a force that this wire experiences. So two wires next to each other are going to exert forces that either attract, repel, or maybe do neither, depending on their orientation with each other. So the problem we're about to go into takes a look at that, and it's a really good way to start practicing all of the gymnastics you have to do between your different right hand rules. So let's try it out. All right, last example here, it has to do with the thing we were just talking about, two parallel wires exerting forces on each other. Now in this case, kind of like with electrostatics, normally when you're working with a charge and then a charge experiencing an electric field, you want to designate one as the source and then one as the experiencer, I guess, if you want to call it that. So in this case, the left wire is going to be the one that acts as the source, and the right wire is going to be the one that experiences the field created by the left wire. So in this case, we have two parallel wires. We say that they both have some kind of length L, and they're both carrying the same current I in opposite directions. Lastly, the wires are a distance d apart from each other. So I'll go ahead and draw that here, that this wire is a distance d away from our source. Now in part A, our goal is simply to draw the direction of the magnetic field vectors produced by the left wire on top of the right wire. So technically, even though we don't really need to draw the magnetic field vectors anywhere else, it's still helpful to think about what's going on all the way around the wire. Our first task here is to put a thumbs up and establish the direction of the magnetic field due to the left wire. So in this case, the thumb is pointing up, and that's exactly where it needs to be, since the current is already traveling upwards. So in this case, you mostly just need to look at where your fingers are relative to the left of your thumb, and then if they were to curl around, where they would be pointing to the right of your thumb. So with the fingers curling to the left of your thumb, your fingertips are going to be coming out of the page. And then if you were to continue curling your hand and your wrist and your finger around, when your fingertips are now to the right of your thumb, they should be pointing into the page since they've done a full loop around. So to the left of the wire then, we are going to have magnetic field vectors pointing out of the page, which I will designate with, let's say the color red. So out of the page is designated with dots off this way. And then when the magnetic field line kind of loops around to the other side, it's going to be designated with X's over here. And so on place of the wire, nothing's really going to change if we were to go further out. And so on top of the wire, our magnetic field vectors are going to be X's pointing into the page. The arrows are flying away from us. All right, so that is part A done. Our next task is to draw the direction of the force that the right wire experiences due to the left wire's magnetic field. So in this case, we need to use a slightly older right-hand rule from the previous video. That's the one that looks more like a finger gun. So in this case, remember that this right-hand rule calls upon the index finger to be the direction of current, or the direction of the charge's velocity, if we've got a lone charge. The middle finger is going to be the direction of the magnetic field that this left wire has produced. And then once you've got those two vectors lined up, your thumb should point in the direction of the force. So our first task is to establish the current direction. So I'm going to take my index finger and simply align it downwards with the direction of the current in the rightwards wire. Once I've done that, I'm going to stick out my middle finger and I'm going to rotate my hand until it points into the page. And so in this case, I kind of have to contort myself here, but I've got my index finger pointing down, and my middle finger should be pointing into the camera in this case, so into the screen if you're looking at it from your own perspective. Once I've done that, my thumb should be pointing at this point to the right from my perspective, which means that this wire is experiencing a rightward force, which I will draw with a, let's say, green vector. So this wire, pretty much all points around this wire, is experiencing a rightward force in this problem. So that is part B done. Now, the remaining two parts here have to do with calculating that force if we would need to. So in this case, the first thing is to write an expression for the magnetic field produced by the left wire. So in this case, all that really is calling upon the equation we talked about earlier. So the magnetic field produced by a long straight wire in general is mu naught, the permeability of free space, times I, divided by 2 times pi times the radius of, or the distance away from the wire. So in this case, if we wanted to kind of put it more in terms of stuff that we were given, it would say mu naught I over 2 times pi times the distance d that's given to us in the problem. This would be the strength of the magnetic field at the location of the rightwards wire. Now the final part here is putting it all together. Say we wanted to calculate the force that this right wire is experiencing in total. Our goal now is to write an expression for the magnetic force experienced by the right wire in terms of the given information. This last part here is cut off for some reason, but always with AP, express your answer in terms of the stuff that you're given originally. So in this case, first we need to recall the equation for force that a wire experiences due to a magnetic field. So the force that a wire experiences, I'll go ahead and color code in green here, is given by the current in the wire times the length of that wire. In this case, really just times the magnetic field strength B. Now, normally, again, this equation is a cross product, but here, just based on the vectors that are shown, all of these things are perpendicular to each other. So the cross product is going to be at its maximum value, or when the sine of theta associated with that cross product is equal to 1. So in this case, ILB is what you can use if they're all perpendicular. Now, in this case, all we need to do is take the magnetic field expression that we got in the previous part and plug it into this equation to round out our day. So here, we'll go ahead and do that. We've got really the same current times the length of each wire times the magnetic field strength at each location along that wire, which, assuming there's no funny business going on the ends of the wires, is going to be mu naught times the same current I divided by 2 times pi times the distance between the wires. Now here we can technically simplify a little bit. We can combine these currents together. And so mu naught times L times I squared divided by 2 times pi times the distance separating the wires is our final answer. So if we took all of our given information and plugged it in this equation, we would instantly be able to figure out the force that one wire exerts on the other, if they're long and they're parallel to each other. So that's really all there is to it. I would say one of the trickier parts of this problem is just making sure you have a good handle on all of your right-hand rules that are starting to pop up in this unit. Believe it or not, that is not the end of new right-hand rules that we'll be covering. So prepare for those in the future. But for now, that is all you really need to work through the basics of magnetic fields and magnetic forces. So from here on out, we're going to cover some more complicated rules and some nice symmetry rules for magnetic fields, and cover the next step in electromagnetism. So until then, thank you very much for watching, and I hope you have a good one. Farewell.